Okay, welcome to Easy Concept. Today we are going to see the RCC short note lecture series, Bond and Anchorage. This is the next one. Okay. So first of all, we are going to see what is bond. Okay. So introduction, the sufficient bond is required between the reinforcement and the concrete. So between the reinforcement and concrete to prevent any relative movement and proper detailing of reinforcement is required for full utilization of member strength without any premature failure. Why we require a bond? In order to create a strong bond between reinforcement and concrete. Suppose there is a element, concrete element, and here there was a reinforcement. Okay, and here is a concrete. So there was a sufficient bond between these two, concrete and steel, so that it will not it will not happen the premature failure. Okay, suppose if there is no bond between these two, then there was a premature failure. Okay, bond means, this is the point important, adhesion between steel bars and surrounding concrete. Bond stress is the shear stress. See, be careful. Bond stress is the shear stress at the interface between concrete and steel, which is denoted by tau PD. What is the meaning of this? It's a shear stress. For example, there was a simply supported beam, and over that there was a UTL acting throughout this span. Okay, and this is the bending moment diagram. If we consider between two sections X and X, and at this point there was a moment M, and here there was a moment M plus dm. This is M, this is somewhat more, right? M plus dm. And here there was a moment, the amount of dm moment is unbalanced. This M is balanced by this M, clockwise and anti-clockwise, but this dm is not balanced. So this dm over a distance of dx. So dm by dx is equal to what? Shear force. So whatever change in bending moment between these 2 points, that is equal to shear force. So corresponding shear force, what kind of stress will be at? Shear stress. So bond stress is a shear stress. Okay, bond stress is a shear stress at the interface between concrete and steel, which is denoted by tau BD. Now, bond stress is dependent upon, here each and every point is important, grade of concrete, zone of placement of steel, whether it is a compressive zone or a tensile zone, and the type of steel bar. It's a HOST bar or mild steel. Okay, this is also important for your examination. Now, bond between concrete and steel is dependent on. So bond between concrete and steel is dependent on, first one, adhesion between concrete and steel. So this is important property. Next is a friction between concrete and steel. Then mechanical deformation of steel bar, whether it's a twisted bar or a plain bar, so on and so forth. Okay, then how we can increase the bond strength? The increase in bond strength by grade of concrete, deformed bars, smaller diameter of bars, higher cover, nominal cover, reducing the spacing of the stirrups, then mechanical anchorage. Okay, so by these 6 we can increase the bond strength. Now, how the failure is happen? Bond failure is happen. Okay, this also an important examination question. First one, breakup of, this is the step-by-step procedure. First will be happen breakup of addition Okay, between bar and concrete. Okay, breakup of, I can write this is the adhesion, breakup of adhesion between bar and concrete. For example, there is a bar for the concrete beam. Okay, bar over the concrete beam. Okay, this is a bar. Now see, first of all, what happened? We know that bond means there was adhesion between concrete which was present here and the steel, right? And the steel, concrete and steel, the adhesion between concrete and steel. Understood, right? Is it okay? Now, in the first step, this adhesion getting break. That means there is a break between concrete and steel. So there was a gap. Okay, there was a gap. So this adhesion getting break. Now, next one is a crushing of concrete in front of ribs of bar. Ribs means, for HOST bar, for HOST bar, there was a provision, it was something like that. This is a HOST bar. This is the rib, for a twisted bar. So this region is the rib. So whatever concrete or cement paste which is present here, that will break up. Okay, that is a crushing of concrete in front of ribs of bar. Next one is a splitting of concrete along the reinforcement. Final step is, first step is adhesion will be getting over. The final step is splitting. Splitting means simply a crack between concrete and steel. So it will be happen along the length of the bar. Okay. Now we are going to see what are the types of bond. First one is the types of bond is the flexure bond, and the second bond is Anchorage bond. Anchorage bond. Now see what is the flexure bond and what is the Anchorage bond. So we will see one by one. First one is a flexure bond. First one, flexure bond. What is a flexure bond? It develops due to variations in bending moment. Bending moment along the reinforcement. RF means reinforcement. Okay. In other words, in other words, presence of shear force, presence of shear force produces flexure bond. Presence of shear force produces the flexure bond. So let us explain this. The flexure bond, I can explain the next slide. So this is the thing. Here, this is the center to center distance between the support. And here we are having a tension reinforcement. Okay, this is the tension reinforcement. Okay, and it is subjected to a UDL load. Okay, now we know that bond between this concrete and steel in the portion of the bending moment. So the bending moment will start from the center of the reinforcement. So this is the bending moment. Okay, so the bond which was happened between the all along the length of the bending moment portion, we will call it as the flexural bond. So we can say the bond which was happened between two support all along the length is called it as a flexural bond. Understood? This is the flexural bond. Keep in your mind. And one more point we said, it is due to variation in bending moment along the reinforcement. What is the meaning? Suppose if we consider a two section, 2 point, this point number one and this is next point. This is the next point. In between those two, here moment is equal to 0. Here bending moment is equal to m plus dm. That means m0 and here small variation, that is dm. Then if you calculate the stress on this steel, tension steel, okay, the stress corresponding to this bending moment is bending stress. So the steel takes the tensile force. If you calculate it, then you will get the force corresponding to moment is T. The force corresponding to dm is dt. Similarly here, the force corresponding to m is T. But here T value is equal to 0 since moment is 0. Here also T value is equal to 0 since moment is 0. Plus the variation is only dm. So finally, this steel bar subjected to a tensile force of dt. Now the dt force which is acting in this direction by an amount of, we know that 0.87 Fy ast. So in order to counteract, this is the force which is acting in this direction. To counteract this tensile force, there was a bond. There was a bond stress shall be developed along the surface of the bar. That is tau bd. Tau bd. Tau bd means what? It's a bond strength. Okay. Now bond. This is the bond stress. Okay. Now the force which is developed corresponding to the bond stress, which shall be equal to the action force, that is dt 0.87 Fy ast. Okay, so this is the thing about the flexural bond. So flexural bond is comes due to rate of change of bending moment, that you have to keep in your mind. Rate of change of bending moment along the reinforcement. In other words, presence of shear force produces flexural bond. Okay, presence of shear force, how can you say? Since we know that this distance is, for example, dx, what is the variation of bending moment between these two? Dm by dx equal to shear force. Okay, okay, this is the answer. I hope you understood. Now the shear stress which was acting all along the periphery of the bar, we can call it as, simply I am writing here, tau. Now this tau, which was finally calculated by getting these two and finally calculate tau is equal to V divided by N pi phi into lever arm, where phi is equal to what? Dia of bar. So that is a mean. Okay. If footnote, if tau is less than tau BD, then no bond failure. So here whatever developed tau which is greater than tau BD, that is a limited, then there is a bond failure. If this condition is satisfied, then there is no bond failure. So tau BD for a different grade of concrete FCK, tau BD. For M20 concrete, M25 concrete, M30 concrete, M35 concrete, M40 and above. And this value is 1.2 and this value is 1.4, 1.5, 1.7, 1.8. So this is the value. Understood? This is the tau BD maximum. Okay. Now this tau BD shall be increased. Note. 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 Point number 1. This tau BD, okay, tau BD has to be increased by 25% due to presence of compression. Due to presence of compression, so okay, that is the bond stress of tension zone is increased by 25% for compression zone. 25% for compression zone. That is a bond stress tau PD in the tension zone, not tension zone, in the compression zone. Yeah, bond stress of tension zone, that is correct. Bond stress of tension zone has to be increased 25% of compression zone. This is the first one. The second one is increased by, the bond stress has to be increased by 60% due to presence of deformed bars. 60% due to presence of deformed bars. Next one, in no case in case of bond failure, most economical way to make a structure in bond is providing more number more number of bars of smaller diameter. This is the important examination question. How can we can increase the bond stress? Bond stress can be increased by providing more number of less diameter of bar. That is smaller diameter instead of less number of bars of larger diameter. So this is the answer. I hope you understood. Now these two, let me explain. For example, see, the tau BD increased by 60% due to presence of deformed bar. Okay, so the meaning is, for a mild steel, that is Fe 250, the tau BD and M20 concrete, let us consider M20 concrete. Tau BD is equal to, what is M20 concrete tau BD maximum? 1.2. That is okay. This is the answer in tension. So whatever this tau BD which was given in the code IS 456, this is only for a mild steel in tension case. Be careful. In tension, this is only for MS in tension. Now it can be increased if it is a mild steel. Instead of mild steel, if you use a deformed bar in tension itself, this bond strength will be increased by an amount of 60%. But in a compression, if you use, okay, only for compression, the mild steel, this value will be increased by 25%. But if it is a deformed bar in compression, then this 25% for only the compressive zone and 60% for a deformed case. Therefore, this value into 25% into 60% increment. Okay, let me explain this here. Tau BD is equal to 1.2 in tension. Now, tau BD is in compression. 1.2 into how much percent you have to increase? 1.25. That is 25%. 25% in compression. Now the same bar Fe 450. That is a deformed bar and M20 concrete. And this will be increased now. The same tension, the tau BD, the same tension here, tau BD is equal to, we are using this bar in the tension zone. Okay, and the tau BD of mild steel will be increased by 60%. That is 1.6. This is 60%. Now the same bar which was used in compression, therefore tau BD is equal to 1.2 into 1.25, that is 25% for compression, into 1.6, that is 60% for deformed bar. So this is the value. So go through this, you will get an idea. Okay, so the bit we finished the flexural bond. Now we are going to see next one, Anchorage bond. Anchorage bond. So the Anchorage bond is this. Okay, there was a reinforcement which was used this and this. Anchorage bond is denoted by a letter L naught. Okay, and not a L naught, anchorage length is L naught, and this is L naught. Okay, this anchorage length. We can say this is anchorage length. So that is a thing. And here, what this is the steel, right? In this steel, if you see the stress, okay, in this steel, okay, this is the anchorage bond which is acts in this direction. This is the tension force. Okay, now what is the anchorage bond? Which one is responsible for this anchorage bond? We are going to see. You can see these bond stress developed around the bar to provide proper anchorage so that reinforcement attains its desired stress. In the diagram L naught provides for anchorage of reinforcement only. Anchorage of reinforcement only. So bond stress around reinforcement in this portion. So the bond stress around reinforcement in this portion is anchorage bond. Okay, now important note this is that is anchorage bond. Anchorage bond is not due to bending moment variation. It is not due to bending moment variation. But the flexural bond is due to bending moment variation. Anchorage bond is not due to bending moment variation. Be careful. These bond stress are developed around the bar to provide proper anchorage. The bond stress will be developed around the bar to provide the proper anchorage. Okay, only this length and bond for proper anchorage of the steel with the support. This anchorage bond stress or anchorage length is not required for resisting the unbalanced tensile force. That means this tension. Okay, but the flexural bond, which is for not for the purpose of anchoraging, it is only for purpose of unbalanced this bending moment. What is unbalanced bending moment? Here m plus dm. There was a variation bending moment. To counteract this variation bending moment, there was a bond stress shall be developed around the steel bar. Okay, so that is important. This is about anchorage bond. Now we are going to see The holistic view of this bond length, and here this bond length. So that bond length is called as a development length. This is the general concept. Okay, we are going to see concept of development length, that is LD. So this is very important. So we can write minimum length of reinforcement is required. Minimum length of reinforcement is required to be embedded in concrete for development of permissible stress in reinforcement. What is a development length? It is a minimum length of reinforcement required to be embedded in the concrete for development of permissible stresses in reinforcement. What is a permissible stress in reinforcement? 0.87 Fy AST in limit state method, comma sigma st into AST in working stress method. So how much length is we have to embedded within the concrete so that that embedded length produce a force which is equivalent to the tensile stress of 0.87 Fy AST in the limit state, and AST sigma st AST in the working stress method. Okay. For example, this is a block, concrete block, and there was a bar. Okay. And it's a bond stress. This bond stress is tau bt. Okay, so it is occur over a distance of development length LD, and this bond stress, okay, that means the total force due to bond stress, which will be equal to the tensile force. T is a tensile force which is equal to 0.87 Fy AST or sigma st AST. This is in the limit state method, this is in the working stress method. That is the thing. Okay, so in equilibrium we can write, in equilibrium we can write the force due to bond stress around the bar, which is equal to tensile force. So we can write tau bt is a stress. What is surface area? Surface area is equal to pi into d into development length into n, which is equal to 0.87 Fy AST. So this is the final value. We know that 0.87 Fy AST, pi by 4 into d square. This is tau bd n pi 5 into LD. So this is the thing. Now what is LD? LD, which is equal to AST divided by tau BD into 4. This is under limit state method. Okay, this is under limit state method. In limit state method, in working stress method, this tau BD into n pi 5 into LD which is equal to sigma ST into AST. In a similar manner, if you do it, then LD, that you will get sigma ST by AST divided by 4 tau BD. Here only sigma ST, but here 0.87 F5. This is the yield stress, sorry, permissive stress in limit state. This is the permissive stress in working stress method. Understood? So this is in working stress method. Okay. Now we are going to see the development length of this. Development length of each bar shall be increased in bundling condition. Suppose if you provide a bundling of bars, so the bundling of bars, then the development length further increased by an amount of 10% in case of 2 bars in one bundle, in case of 3 bars in one bundle, then 20% will be increased, then 4 bars in one bundle, then 33% will be increased. This is important examination question. Repeatedly this was asked. Okay, this is due to bundling of bar. Now, diameter of bar used in one bundle condition shall not be more than 32 mm in case of beam, but in case of column more than 32 also. So this is a bundling of bar, right? In that, one bar diameter should not be more than 32 mm in beam, but in column it can be more than 32 also. Understood? Now this is the bundling of bars. Because of the bundling of bar, how the development length is increases. Okay, and the next one is how to provide this anchorage length. Way to provide values of way to provide anchorage length. Way to provide anchorage length. The first one we are going to see by providing development length. That's the first one. Okay. First one. Yeah. By providing development length. So how? Suppose we will provide this anchorage length in terms of development length. This is the cantilever bar. In that cantilever, we have to provide anchorage length at least from this edge of the support to here and this one. Okay, this shall be at least LD, and this one up to here at least LD shall be present. Okay, So this value should not less than, and this also you have to provide at least, that is this value should not less than L2. This is by providing development length. Okay, by providing development length. And one more case, in case of a smaller cantilever portion, this portion, this thickness is very small. Here the thickness is somewhat big, but here the thickness is somewhat less, the cantilever beam. And here we have to provide the anchorage length in such a way that you start from the phase 2 here, it will comes and goes something like that, and from here to here it will goes, and you can provide this. This is the anchorage length that you have to provide within the support. This is the anchorage length you have to provide on the beam, and this value also should not less than LD, and this value also should not less than LD. This is for small cantilever. Then note, we have to write some of the note point. Note, in case of or in no case, distance between point of permissible stresses in a reinforcement and ends should not be less than LD. Should not be less than LD, meaning suppose this is the starting point of this much length. This is the starting point, and or this is the starting point and this is the end point of the development length corresponding 0.87 F5 AST, meaning this much development length is required. This much development is required to counteract this tensile force of permissible tensile force of steel. This is LD. This value should not less than LD. Okay, so this is equal to, I can say this is the, for example, I can consider the 0.87 Fi is starting here, 0.87 Fi AST. Therefore, I can call it as this is end point. This is one. And the similar manner, suppose in the left side, this is the starting point, and this is the end point of bar, and this value also should not less than LD. This is important. Okay, and the next one is, this is the case A. Now case B. By providing values of bonds, values of bends and hooks, values of bends and hooks, that we are going to see first. We know that LD required, which is equal to LD straight minus anchorage value, that is AB. What is the meaning of LD straight? Here, if you provide a bar for anchorage purpose in a straight manner, then we required LD. The length we required is LD for resisting a force of 0.87 Fy AST. But in some cases, we can't able to provide, we can't get that much length of development length in order to develop a bond stress. For example, the development length which is required for resisting this 0.87 Fy is, for example, 1000 mm or 700 mm. But here, in the above slide, in the last stress we having seen, from this point to this point, we required LD at least. But here the thickness is only we are having, for example, 300 is a width. But 700 mm anchorage length is required. But here 300 is only available. Then what we can do? You can bend this and you can provide a length something like that. Now see, this length is LD. This is the LD, but you know this LD is, in that LD, this bend itself, only this bend, that is an anchorage value. This bend takes a value. This bend takes some value. Depends upon the angle, there was a value which was there. Okay. So LD straight means, this is the LD straight. LD, this is the LD straight. Understood? Now, because of this 90 degree bend, there was an anchorage value which is 8 pi. Now, LD required is equal to how much? LD required is equal to 700 minus 8 into, for example, 10 is the 5. Let us consider 10 millimeter diameter bar. So is equal to how much is required now? 620 mm is enough. 620 mm is enough to anchorage this bar within the support. Actually 700 is a LD straight is required, but this LD straight is not possible to provide. If you want to provide LD straight, then it shall come somewhere here. This is LD straight. Okay, but it's not possible to provide because only 300 mm thickness. That's why we are making a bend and inserting vertically. And while making a bend, that bend, it takes some anchorage value. That value is 85. Depends upon the bend, there is a value. Now I'm going to give anchorage value and the bend. Anchorage value and degree of bend. Degree of bend. Anchorage value and degree of bend. Okay, the anchorage value, that is AV. Degree of bend is 45 degree, 90 degree, 135 degree, 180 degree. What is anchorage value? Anchorage value is equal to 45, 85, for 90 degree 85, for 135 degree 12.5, for 180 degree 16.5. To keep this in your mind. Okay. Important examination question this. In the state government, you can expect this value itself. Now, note. note, note, more than 180-degree bending is not allowed. Is not allowed in concrete. More than 180 degrees not allowed in concrete. Okay, this 180 degree is bend is called is a hook, U type hook. Also it is called U type bend, U bend. It is U type bend. Okay, next one. 180 degree hook is possible only for mild steel. Okay, for HYSD bar maximum allowed is 135 degree. So that is the thing. Understood? Now we are move on. Anchorage length for stirrups. Next under the note anchorage value for anchorage value for stirrups. Anchorage value of stirrups. The first one for 90-degree bend, 8 times the dia. For 135-degree bend, 6 times the dia. For 180-degree bend, 4 times the dia. Okay, this also you have to keep in mind. Anchorage value for stirrups. This is the anchorage value of straight bar. Okay, now we are going to see some of the important points under this bond and anchorage. What is what? First one, containment of flexural reinforcement. So these all are, now we are going to see some of the important points. Those all are required for your examination. Here's only the statement they will ask you. In the statement and the factual data they will ask you directly, you can attend the question. Okay, once you read this statement very carefully. These all statements are IS 456 2000 says for curtailment of flexural reinforcement. You know what is a flexural reinforcement? You know that flexural reinforcement means the reinforcement which was used under flexure. Here, yes or no? And we know that this reinforcement, this is the reinforcement. We don't want to use the reinforcement throughout length. Since the Bendiment diagram is maximum at the center. Okay, this is the beam and this is the Bendiment diagram. The bending moment is gradually reduces from center to extreme. So this is the maximum point and you have to provide a reinforcement here, bottom. This is the bottom reinforcement, the reinforcement shall be provided at the center and you have to bend or you have to curtail beyond a certain position, certain portion. You don't want to put the entire steel up to the end. Why? Here the moment is less. Okay, so if you see in the cross section in the plan, if you look in plan, if you look in plan, Okay, I'm going to draw this in the plan. So you have to extend in top view. Okay, top view. In top view, suppose if you are going to provide 4 bars, then you have to extend 2 bars up to the support, 2 bars up to the support, and this is a 1 bar. This is another bar, and this is the another bar. This point is called curtailment. It's a cut-off point. This point is the cut-off point. This point is called cut-off point or curtailment point. Only certain percentage of steel only extend up to support. Remaining we have to cut. Why we are cutting? So we are cutting for economical purpose. That is our main motto. Now see, bars of fluctual tension are deemed to be curtailed or cut off beyond the point it is no longer required. Beyond this point, it is not required. Curtailment is done after satisfying the codal provisions. Very, very important. First one, according to IS 456-2000, there are certain rules to be obeyed for curtailment of steel bar. There are certain rules shall be obeyed for a curtailment of steel bar. First one, at the curtailment section, that is a theoretical cutoff point. Means this is the theoretical cutoff point TCP. All steel bar must be extended for a length equal to 12 times the dia of bar or effective depth, whichever is greater. See, this is the theoretical cutoff point TCP, but you don't curtail this TCP point. You have to curtail, you have to extend this bar up to a distance of actual cutoff point, and this distance you have to extend 12 times the dia or effective depth, whichever is greater. Very, very important. Now, second point, flexural reinforcement shall not terminated in tension zone unless you shall not terminate the tension zone unless any of the following conditions are satisfied. That means the flexural reinforcement you shall not terminate. It means end unless the following conditions are satisfied. If the following conditions are satisfied, then you can terminate in the theoretical cutoff point or whatever point you want. But if the following conditions are not satisfied, then you should not terminate here. You have to extend up to the end. First point. If this condition is satisfied, you can terminate. Otherwise, you should not terminate. First point. At the curtailment section, that is the curtailment section, that is actual cutoff point, the external shear force. That means at this point, shear force due to external load shall not exceed 2/3 of the capacity of that beam at that section. Okay. At this point, there was a shear capacity of this section and external force is there. The external shear force is, for example, 10 and the shear capacity is, for example, is equal to 15. If the shear capacity is this 15 and the external shear force is 10, then this is the 2/3, right, of this? Yes or no? So the condition is, what they say is, you don't want to terminate if the shear capacity of this section or the external shear force coming on this section is 2/3 of the shear capacity. For example, the shear capacity of this section or the external force which is coming on the section is, external force is 10. Okay, this shall be not more than, this 10 is not more than 2/3 of the shear capacity of this section. Okay, you have to find out the shear capacity of this section is, for example, 100. Let us take 100. Then what is the shear capacity for two-thirds of this 100? That is a 200 divided by 3. So this 200 divided by 3, we can write it 66.67. So 66.67 is a two-third, meaning you can allow the external shear force up to this 66.67. You should not encourage the load more than 66.67. That is a meaning. Okay. So at the containment section, the external shear force shall not exceed two-thirds of the shear capacity of the beam at that section. Next one. Suppose if the section at the actual cutoff point is more than, suppose it is exceeded, in the last case we having seen 100 is the shear capacity, two-thirds of 100 is equal to 66.67, that is external shear force. Suppose in this point this external shear force is greater than 66.67, then what we can do is greater than two-thirds of shear capacity, then excess shear stirrups are provided along the terminated bar for a distance of 0.75 d. For a distance of 0.75 d from actual cutoff point, and the area of stirrup shall not be less than, and the area of stirrup shall not be less than this value. Meaning, from this point, this is the actual cutoff point. From this actual cutoff point, this is, for example, somewhere here is the actual cutoff point. Then here the shear capacity is, external shear force is greater than two-thirds of the shear capacity. Then you have to put the additional shear reinforcement closely for a distance of 0.75 times the d. Understood? So that's a point. And this value, this ASP should not be less than this condition. This is the codal condition. Next one. For 36 millimeter or smaller bars, and the area of steel is twice of the requirement for flexure at the cutoff point, and the shear force shall not exceed T 3/4 of the shear capacity. This is the next point. Next one, the distance between curtailment of individual bar in bundle shall be 40 times the diameter. The distance between the curtailment of individual bar. Okay, this is one bar, and this is the another bar. This is the curtailed bar. This is the full bar. The distance between curtailment of individual bar in bundled. Okay, in a bundle means this is the one bar, and this bar is curtailed, and this is the another bar. Therefore, the distance between these two shall be 40 times diameter of bar. Understood? This also you have to keep in your mind. Now we are going to see what is a positive tension reinforcement. Okay, as per IS 456 2000, at a simply support where sagging moment is very low, at a simply support, at least one-third of total reinforcement required for positive bending moment must be extended inside the support for a length of not less than LD by 3. In case of intermediate support, at least 1/4. Simply support 1/3. Intermediate support 1/4 of total positive steel must be extended inside the support for a length not less than LD by 3. Okay, so I can draw a diagrams for better understanding. Suppose bar. This is the intermediate support. This is the simply support, extreme support. And your bending moment diagram, for example, in this case, it goes something like that, because this is the UTL. What code says, this is the simply support. This is the intermediate support. The AST that you have to extend, for a length of, this is the simply support. The positive reinforcement, this is the positive reinforcement, right? This value for intermediate support, you have to extend up to a length of LD divided by 3, and this value AST is equal to actual AST divided by 4. Here you have to extend for a length of LD, and this value is AST divided by 3. For a simply supported end, you have to extend this LD divided by 3 distance by a minimum amount of AST by 3. Here you have to extend in the intermediate support for a distance of LD by 3 by an amount of AST by 4. Okay, so that's the thing. Next one, at a simple support, the point of inflection. So this is the beam. If you draw a bending moment diagram, this point is a inflection point. Inflection, at the point of inflection, the positive reinforcement shall be limited to a diameter such that at the inflection point, the limited diameter as per IS 450 says, such that the following condition must be satisfied. Very, very important. At the simply support, the LD, the anchorage length that you have to provide, 1.3 M1 divided by V plus L naught. At a point of inflection, LD is equal to M1 divided by V plus L naught. This is the from inflection point to the center of the support is L naught. This is from center of the support to the extreme is, this is the L naught. The L naught is measured. Then I have written, what is L naught? This anchorage length beyond the center of the support, including equivalent anchorage value of bend or hook and mechanical anchorage for simply supported end. For a simply supported end, this is the mechanical anchorage. Mechanical anchorage is provided something like that. There is a arrangement. Okay, this arrangement is called as a mechanical anchorage. Okay, M1 is the moment of resistance of section at a mid top simply supported beam and point of inflection respectively. This M1 at a simply supported M1. This is the M1 is the at a point of moment at a point of inflection. Here moment at a simply supported end. We also same shear force at the center of support and point of inflection. Now note factor 1.3, which was used in case of value of N1 divided by B by 30% is used for simply support to counter for confinement of concrete due to compressive reaction. Now negative tension reinforcement, positive tension reinforcement is over. Now negative tension reinforcement. In case of negative tension reinforcement, at least 1/3 of total reinforcement shall be extended beyond the point of inflection for a distance whichever is greater of the following: 12 times the diameter of bar, effective depth of the beam, 1/16 of the clear span. This is the explanation. Suppose this is the intermediate span. Here we are using the reinforcement at the top. This is the reinforcement we are using at the top. This is the center support. Now this is the bending moment diagram will get. This is the positive bending moment, this is the positive, this is the negative. Now this is the point of inflection. You have to extend this negative reinforcement from the point of inflection by an amount of AST by 3 at a distance of effective depth of the beam, or 12 times the diameter of the bar, or 1 by 16 times the clear span on both the end. Is it okay? Now next important is splicing. What is a splicing? Splicing is a connection joining a bar of a standard length to get a bar of desired length is called splicing. Suppose you want the desired length is, for example, you want a 20-meter length, but your standard length available in market is, for example, 12 meter, for example. Then how to make this desired length? By joining a bar. This is one bar, this is the another bar, and this entire length is called as 20 meter, and this is called as a lap length, LP. This is LP is equal to lap length. Understood? According to IS 456, there are certain rules to be obeyed for splicing of steel bar. This process is called splicing. Okay. At the splicing section, this is the splicing section. The external bending moment must be less than or is equal to 50% of moment of resistance. This is important. Or you can say the moment of resistance at the splicing section shall be 2 times the external bending moment. Then at one section, more than 50% of total steel bar shall not splice. At a single point, at a single section, at a one section, you should not splice more than 50% of bar. Okay, that means number of splicing of bars shall be less than or is equal to 50% of total bar. The diameter of the bar shall not be more than 36 mm. Be careful, very very important. If it is more than 36 mm, then we can go for welding. If the diameter of bar is more than 36 mm, then we have to go for welding. Now, the spacing of staggered splicing shall be greater than or is equal to 1.3 times the lap length. Staggered means the lap length. So this is the in plan. We are doing a lapping. So this is one bar, and this is the another bar. In one section, you lap. Now the staggered lapping is something like that, and this is the another splicing. So here this is the lap length somewhere here, and here this is the lap length, and the distance between these two, I'm saying this is the staggered. This distance is 1.3 times the lap length. They are saying spacing between staggered splicing 1.3 times the lap length. Okay, so this also important. Now the next one is the splice length or lap length. Okay, shall be 30 times important state government examination of smaller diameter of bar or LD, 30 times diameter of bar or LD, whichever is greater in case of flexural tension, where the straight length of splice without bend or hook shall be 15 times the dia or 200 mm, whichever is greater. Next point, the lap length of direct tension member, this is the flexural tension, this is the direct tension, 30 times diameter of bar or twice the LD, whichever is greater. The lap length for compression shall be 24 times the diameter of bar or LD, whichever is greater. Read carefully. Now, if two bars are of different diameter, then smaller diameter shall be adopted for finding lap length. This is also important thing. Understood? So with that, we have been finished the bond and anchorage. Okay, and we will see in the next lecture series some other topic for short note. So thank you for everyone.